of the most common applications of calculus involves determining maximum and minimum values. Like, how do you maximize on profits while minimizing cost? There are plenty of examples where optimization is applied. The procedure is to choose variables and/or draw a labeled figure, write a primary equation, we're going to call it the objective equation, isolate whatever it is that needs to be maximized or minimized, rewrite with only one variable on each side. This may require a secondary equation, and if we need a secondary equation, we'll call that the constraint. Find the domain, take the derivative, find critical numbers, make a number line, and then find your max or min. A box with no lid is to be made from 48 square centimeters of material. If the box must have a square base, find the dimensions that produce a maximum volume. So first of all, what are we trying to optimize? That is our objective equation. We're trying to optimize volume. Now, the volume of a rectangular prism is length times width times height, but it just so happens that they wanted a square base. So if this side is S and this side is S, and this is our height, then our volume is S squared times H. What kind of information did they give us? They also gave us the surface area of the box. We will call this equation our constraint because it will help us to solve for one of our variables. Surface area of this square-based box is the area of the bottom, which is S squared, plus the area of each side, SH, and there are 4 of those. Now, we know that the surface area is actually 48, so I'm going to plug in 48 for the surface area. At this time, we need to rewrite our objective equation with only one variable on each side, and right now we have 1 on the left side and 2 on the right side. So I'm going to solve for either S or H in the constraint and plug it in to the objective equation. It looks like H is a lot easier to solve for than S. Now that we've solved for H in our constraint, we can plug it in for H in the objective equation to make the objective equation only have 2 variables. Simplify. We have now rewritten our objective equation, so now it has 1 variable on the left side and 1 variable on the right side. Now we determine the domain. Finding the domain just means looking at it through the relevance of this problem. We're not going to be looking at negative side lengths or negative heights. And because we're maximizing the volume, our domain will be greater than 0. Now we can derive, make our number line, and determine our relative extrema by evaluating the derivative of v with respect to s. This is the derivative of the function we are optimizing. Now we'll find critical numbers. Critical numbers are when the derivative is equal to 0 or undefined. This is a parabola, so it's not undefined. And we'll solve for s. Now I put plus or minus 4, but we know that negative is not really a side length that we're looking for. So really, s should equal 4. That is our side length for optimal volume, but is that maximum volume? Let's check with an f prime number line, or in this case a dv ds or v prime number line. If I evaluate dv ds at s equals 2, I'm going to get a positive value, 12 minus 3. I'm going to get a positive value. If I evaluate the derivative at s equals 5, that will end up giving me a negative interval for the derivative, which means decreasing for the volume. All right, so it looks like we have maximum volume at the critical number of 4, a relative max. Our correct side length is 4. If that is the length of the side of the base of the box, what is the height? We already have a relationship between h and s, where I've solved for h. So plug in 4 for s. And our height should be 2. They asked us to answer with a complete sentence. So we're going to say, to obtain the maximum volume, the side length of the base is 4 centimeters and the height is 2 centimeters. For number 2, the product of two positive numbers is 288. Find the two numbers so that the sum of twice the first plus the second is as small as possible. The product of two positive numbers is 288. So I'm going to say x times y is equal to 288. These are positive numbers, so x and y both need to be greater than 0. Find the two numbers so that the sum of twice the first, so 2x, plus the second, is as small as possible. So I'm going to say 2x plus y equals the sum. I have two equations, but which is my objective and which is my constraint? I'm trying to optimize the sum. The sum needs to be the smallest. So this would be my objective equation, and this other equation will be my constraint, which will help me to derive the objective equation. Before I can derive the objective equation, I need it to have one variable on the left side and one variable on the right side. So I need to either eliminate x or y. I'm going to solve for y. Y is equal to 288 divided by x. Plug that into the objective equation. Another way you could write this is 288 times x to the negative 1. Let's derive s, the sum with respect to x. The domain of this function is anything but 0, and our numbers have to be positive. So we already knew that x and y had to both be greater than 0, so don't have to worry about that. So even though 0 is one of our critical numbers where the derivative is undefined, it's not actually one of our possibilities for this problem. And again, negative 12 is not an option, so x has to be 12. The only critical number that is useful to us is x equals 12. So on the number line, again, must be greater than 0. My intervals for ds dx, or the derivative, is negative here, and positive here. So we do have a minimum at x equals 12. Plug in x equals 12 to find y. We already have a relationship between x and y. When x is 12, y is 24. To write our final answer as a complete sentence. To obtain the minimum sum, the first number is 12 and the second is 24.